Good morning, good afternoon, wherever you're joining us from. Today we're fortunate to have a speaker whose career has made important contributions to functional programming. I first encountered Erik's work through a series of interviews he did for Channel 9 at Microsoft, where he explores many interesting topics in computer science with engineers and researchers across the programming language community. I later learned that not only was Erik a great interviewer, but also an innovative thinker and the creator of several technologies I was then using, including Link, a type-safe DSL for data processing, and RX, a concurrency framework for the .NET platform. The ideas he developed have been widely adopted in many domain-specific and general-purpose programming languages throughout the software industry. It was only recently, about 2 years ago, I learned Erik had an interest in automatic differentiation, a topic close to our own hearts here at Mila. We later had the chance to meet at a conference where I discovered he has many interesting things to say about this topic, and I'm eager to learn more about it with all of you here today. Please join me in giving a warm welcome to Erik Meyer.
Well, thanks everyone, and it's my pleasure to give this guest lecture. A little bit of the background of how this all happened. I've been looking at automatic differentiation, probabilistic and differentiable programming for a while, and what I found out is that a lot of the literature, traditional calculus literature, I didn't really find that great. A lot of it is just copied from each other. If you go online, for example, if you look for calculus books, intro calculus books, right, for colleges, they're all like basically copies of the same book. And I don't think it's explained very well. So that's what I set out to do. So there's nothing really new here. There's nothing new here, and that's by design. So what I'm really trying to do is trying to explain calculus concepts as if my audience is like a kindergartners, 4-year-olds, and trying to make everything super trivial. So if you kind of come away today with that sense, like, oh, this is all trivial, then I'm happy. Because that is kind of like how it should be, right? Like we shouldn't overcomplicate things at all. And the other thing, it's also this, I don't know if people have this, I still have them, is these kind of like weird dreams, COVID dreams. And in a lot of these dreams, I end up kind of like dreaming that I'm skipping math classes again. Like my friends are saying, hey, are you going to the exam today? It's like, what exam? Or I get like, don't do my homework. And it's always about math classes. So this is also my way to counteract those dreams. Okay, like maybe they're telling me something and I need to like do my homework better. As I said, like, my team at Facebook, what we're doing is we're using machine learning to optimize systems and to make developers more productive. And then we have a small group that, or two groups that are building programming languages for deep learning or machine learning. One is probabilistic programming language, and if you Google search online, we have quite a few papers on that. We started with adding probabilistic programming to hack. We found out that that was not the right audience. So we switched to have a language embedded in Python called Bean Machine. And then we have a differentiable programming group where we are hacking the Kotlin compiler to add automatic differentiation in a type-safe way. So we have tensor typing, and we're using the fact that we can do things at compile time to optimize things. Now the big And again, you know, if you look at like these things like software 1.0, software 2.0, I think the big difference in this new world of machine learning, whether it's differentiable programming or probabilistic programming, it's all about continuous math. Where in the past, it was all about discrete math. And what I'm trying to do here in this talk is to show that really you can take everything you know about like discrete maths and especially algebra and translate that to this new world. So you don't really have to learn much new stuff, especially if you're kind of like know functional programming, then this new world should be fine for you. Right, so let's get like differentiable programming. Of course, that's about differentiation, automatic differentiation. Some people explain it as some like, you know, some souped up version of the chain rule. Now, what is differentiation? If you look it up on Wikipedia or in books, you immediately run into limits, right? So the derivative of a function is some limit of h going to 0 of this quotient here. And then if you go and zoom in or double click on limit, now you get this dreaded epsilon delta definition for all there exists, blah, blah, blah. And now there's like, you know, this token soup of Greek symbols, and most people's brains at this point melt, stack overflow, floating point exception, whatever. Now, if you look at probabilistic programming, that is really all about integration. So this is kind of nice that there's the kind of like duality between integration and differentiation, and then you see that happening in the programming models too. So differentiable programming is about differentiation, probabilistic programming is about integration. Why is that? Well, if you look at another way of looking at probabilistic programming is programming using the probability monad. And if you look at the definition of bind in the probability monad, that's all about integration. And another way to look at this is that if you want to get like change a density into a probability, you have to take the integral of the density function over a certain interval. So you whatever way you look at it, in order to do probabilistic or probability, you have to get like do integration. However, if you get like, you know, look at what integration means or how it's defined, quickly you end up with limits and epsilon and deltas again. And again, your brain melts for a second time, your stack overflows again. And what I want to show you is that don't worry, and you can do all this without ever knowing about limits and all that crap. And the idea is the following, like real numbers, it's the name is a little bit, I would say, a cheat or a con, right? Because real numbers are actually as not real as you can be, because there's an uncountable number of them. You cannot represent them in a computer, so they're actually not real. They're just, you know, something that mathematicians imagined, and it took mathematicians actually quite a long time to come up with a definition, a standard definition of real numbers. And here is, I think, the one that we got, like, you know, mathematicians use most today. It's Cantor's real numbers. And it's basically an abstract data type. So that's a way to look at real numbers. It's an abstract data type, a set of values a crazy set of values that satisfy certain properties and on which you define certain operations. But then, of course, just like with any abstract data type, you can have multiple ones. And what we're going to do today is we're going to use a different kind of real numbers. And these are ones that are invented by Lauver. And again, like, it defines a set of values with some properties or axioms. And in particular, I want you to look at axiom 4 here on the slide. And it says that these, this kind of real numbers has some special values for which the square of these values equals 0. So another way to say that is kind of like these are nilpotent infinitesimals. And these numbers are, well, this is kind of like, this kind of real numbers leads to some problems if you stick with classical logic, but I'll skip over that. I'll kind of like wave my hands wildly. So think of these infinitesimals as things that are not 0, although that is not really true. But anyway, but these are values whose square is 0, but themselves are not 0. And then there's an additional thing here is that for every function from these infinitesimals to the real numbers, there's a unique value such that f of d equals f0 plus d of a. So in some sense, you can say this is cheating, because as one of the axioms of these of Lauver's numbers, differentiation is built in. That is kind of like axiom 4, right? This says that, like, functions over these real numbers kind of like have derivatives. But that's fine. Again, we're just defining some set of numbers. So I think it's smart, if you want to have a notion of derivatives, to just build that into your abstract data types. Makes your life much easier. You don't have to then kind of introduce weird things like limits and so on. So I kind of like this. So in this talk, if I use the, like, the boldface or whatever R, that's counter real numbers, and if I use the regular R, that is a Lauver's real. So like, keep that in mind. So there's a little bit of a typing system here. But as I said, like these special Lauver real numbers are, they can introduce paradoxes. All right. So if we assume that these infinitesimals, nilpotent infinitesimals, come from the real numbers, then we can show here that 0 equals 1 because of axiom 4. So that is not, that's not a great thing, right? Because now we have an inconsistent system. So Cantor's reals are incompatible with nilpotent infinitesimals. So ultimately, as I said, like one thing what you should do is you should kind of like drop classical logic and you should work with intuitionistic logic. And really what you cannot do is you cannot have the law of the excluded middle. I don't want to get like, make this a point of attention. I don't want us to be distracted by this. So what I'm going to do for this talk is I'm kind of going with something slightly simpler. I'm going to use dual numbers, which are like a scaled down version of Lauver's reals, implemented as pairs of Cantor reals. But everything I do here can be easily extended to Lauver's reals. If you just kind of like stick to intuitionistic logic. So no problem there. All right. So, and by studying dual numbers, it's like the fruit fly here of keeping things simple. You can understand this general theory much easier. And as I said, like everything just carries over, but I just don't want to get distracted by any of these inconsistencies, potential inconsistencies, and so on. So what are dual numbers? Well, dual numbers, probably you've seen these in talks in your series before. They are even older. They are were invented by Clifford in the 1800s. And they are pairs of numbers. And like mathematicians often do, they get like write pairs in weird ways, just like they write complex numbers as pairs, but then use addition as the pair constructor. In this case, it's a pair of a plus a epsilon. I'm using lowercase and uppercase a, lowercase for the real part, and uppercase a for the infinitesimal part. And there, the epsilon is a nilpotent infinitesimal, so epsilon square equals 0. And just like with the lower numbers, you get here differentiation for free, or derivatives for free. So if you take a function defined on the real numbers and you lift that function to the dual numbers, you get a unique dual number that represents the result of the original function and its derivative. So that's like given here in this property. So if I compute f of a plus a epsilon, I get another dual number, f of a plus the derivative of f of a times a epsilon. And if you remember axiom 4, it really looks like a beefed up version of axiom 4, except where the lowercase a equals 0, and then you get exactly axiom 4. But you can also show that given axiom 4, you can define, you can extend it to general functions like this. So these are like, equivalent. So it's really, we're losing nothing by looking at dual numbers, except that we're making our lives a little bit easier. Now, how do you prove that this property holds, right? Because I can claim this, but we have to prove it. Well, you can use Taylor expansion, but that's not really a real solution, because first of all, you assume that Taylor expansion holds, plus you assume that you already know what derivatives are. So that's kind of like maybe works as an intuition pump, but this is not a real proof. Plus the other thing is that we're using Taylor expansion using dual numbers, right? Where Taylor expansion is not typically defined using dual numbers. So this is really not a proof at all. It's really just something like, okay, it makes sense. It's like a smoke test. Maybe what we can do is we can, like these infinitesimals, like intuitively they're very small numbers, so they might be like they're like limits. So let's kind of like, say, okay, let's take the definition of derivatives that we have seen using limits and just replace everywhere where we have a limit of something kind of going close to 0, we're replacing that with one of those nilpotent infinitesimals. Well, the problem there is that it leads to a contradiction again if you allow division by these infinitesimals. So you can prove that epsilon equals 0 if you allow division, the proof is there at the top, which is not that great. So what we're doing here is, what we're saying is, let's assume that we have structural equality on these dual numbers. And if we have structural equality, so two dual numbers are equivalent if their real parts are equivalent, and if their infinitesimal parts is equivalent. And that allows us to drop these epsilons there. And if we just zoom in on the infinitesimal part, we get a rule called micro-cancellation, which says that two of these like infinitesimals are the same if they're like, like A epsilon equals B epsilon if A equals B. So this allows us to eliminate epsilon without doing division. And we avoid the paradox. Now let's look at what we can do now with what we've gotten with these dual numbers, the dual numbers property plus micro-cancellation. Well, we can show the derivative of inverse function, and then we can show the like, typical like or usual thing. The derivative of the inverse of f is 1 over the derivative of f applied to the inverse of f. And don't worry too much. What I really want, I want you to get from this is that this calculation here is super simple. I've spelled it out in all detail, and all the steps are trivial, right? I'm either using simple arithmetic, or I use properties of dual numbers that that they give you the derivative, and in this case I'm using properties that f and its inverse are each other's inverse. So really, what I've done is I can now compute these things using just algebra, right? By just using symbol crunching and symbol pushing. Really, really easy. And that's exactly where I want to be. Same way we can show the sum rule, the product rule, the quotient rule, just by simple calculation. If you look at the product rule, for example, you just take two of these numbers, you multiply everything out, you use the fact that epsilon square equals 0, and voila, you have the usual product rule here. So no need to have limits or anything. Everything becomes just straightforward calculation. And that's what I promised you.
I don't know if you could clarify whether, so you mentioned that it's kind of the symbol pushing paradigm. If do you encounter any issues with rewriting? I mean, if you do these operations in a slightly different order, maybe there's certain benefits for precision or so on. Is that a property, or is this something you don't have to worry about in this system? Thanks.
You mean like numerical imprecisions in that sense?
Yeah, I guess. I mean, so if there's certain issues with that, or if you can get some benefit, by rewriting, or it's just not something you have to worry about.
Now, I would say this is something you always have to worry about, because like floating point numbers, like that's something I shoved under the carpet, right? Because I said like, oh, there's the Cantor reals, there's the Lover reals, but on our computers we have floating point numbers, which are some weird Franken monster that is a finite representation of these uncountable set of values. And when you use them, that introduces all kind of errors. Not all your properties hold. Associativity doesn't hold. I'm going to gloss over that here. But yeah, so like, I'm not sure that this will help you with that, but yeah, stick up, like, you know, always when you translate things that use like real numbers into something that uses floating point numbers, you have to be careful with
yeah,
how that behaves.
thanks.
But again, like for this talk, I'm going to be completely naive about that. Now here are like, you can extend this to, like, you know, sine, cosine, whatever. And really what I want to show here is that in order to, if you introduce a new function and you want to introduce that into this system of dual numbers or lower numbers, whatever you prefer, what you need to do is you need to figure out what the behavior is of these functions on epsilon. Once you have that, then you can just calculate with them. And here you can show, like, you know, that sine of epsilon should be epsilon, cosine of epsilon should be 1, and tangent of epsilon should be epsilon. But once you have that, now you can compute the derivatives of sine and cosine, and you get the usual rules. But really, the most important part is that you know how they behave on epsilon. In some sense, you're kind of like overloading these functions to dual numbers. And that's maybe the intuition, computer science intuition. And when you overload them, you have to like tell how it works on f of epsilon, or really that is f of 0 plus epsilon, right? It's the kind of dual number where the real part is 0. And to take that back to axiom 4, that is kind of like the same thing that's happening there, right? You define what, how f behaves on one of those nilpotent infinitesimals, and then everything falls out. That's the same thing that we're doing here. So you figure out what it does on an infinitesimal, and then everything will work out. The nice thing about dual numbers is that you can implement them easily in code because they are just pairs of numbers. Here I'm using Kotlin. And what you see here is basically just a straightforward translation of the math into code, like just one-to-one translation. That is another advantage of using dual numbers instead of lower numbers, because there you have to, if you really want to implement those, you have to build like trees of dual numbers, and it has to be recursive. So this is just a simpler version. As I said, it's the fruit fly version. Now, this corresponds to forward AD. Of course, for deep learning, we use backwards AD. In different talks, I've shown that backwards AD is really nothing than continuation passing style applied to forward AD. I'm not the only one. Connell Elliott has done this, and many other people. T.R. Grumpf, like, I think this is now well known. To think about, like, you know, the question about the actual numeric computation, one of the things that you're using here to convert backwards AD into, or forward AD into backwards AD, is you're using associativity, which might be a problem numerically, but again, let's gloss over that. I also won't talk about backwards AD. It's more complicated to reason about and to work with. And I'll just wave my hands here and say, it's like, whatever we do for forward AD, we can do for backwards AD after a a more or less straightforward CPS transform. The only trick there is you have to be careful with sharing, which makes everything a little bit more imperative if you're not careful, but for today, we won't bother with that. All right, what we're going to do instead is I want to use a fact that I didn't highlight so far, namely that that if you look at the definition of, or at axiom 4, and also at the definition of dual numbers, like f of a plus a epsilon equals f of a plus f prime a times a epsilon, then f prime a is a unique value, all right? And that is something I think is important, because what we're doing is we're defining derivatives as a universal property, right? Like it's always interesting if you see a definition that says for all things there is a unique value such that, and that's what we're going to zoom in now. And in order to get it clear, we are going to take the defining properties of dual numbers and going to bring that into point-free style. And point-free style, if you're a functional programmer, Haskell programmers love to do point-free style. Usually, and you see it here, if you look at the first line in red, that is the regular version. And then if you look at the one in yellow, that is the point-free style. You see that is like much less readable, but it's now like really captures, I think, things much better. And we'll show the consequences of this, like, you know, this definition later. But let's first, like, given the time, I'm going to skip over how we're actually going to go about putting this in point-free style, except step 0. Because that is a trick that I think is very useful. If you look at Squiggle, I don't know if people heard about Squiggle. This is like, you know, a way of doing program calculations that was very popular in the functional programming community in the 90s, like sometimes called Burt Merton's formalism. And there, this idea of Skolemization plays a crucial role. And what it allows you to do is it takes a formula with quantifiers and turns it into a formula without quantifiers, or with only universal quantifiers, and then you can drop them. And it's like whenever there's an existential quantifier inside the universal quantifier, so in this case for all x, there exists a y, what you do is you replace the y by a function of x, right? So, and that function f will conjure up the y that supposedly exists. And what this allows you to do is that you can write now a lot of formulas that have complicated quantifiers in point-free style. So for example, if you look at the rightmost column here, it says for all x, there exists exactly one y, such that p x comma y holds. A different way to write that is p x y if and only if y equals fx. So that's like the thing that we're going to use.
Erik,
yep.
For that part, is that why you need this intuitionistic or constructive framework? Because you need to construct this example of f and x, or can you make a statement such that it's true that for all x there exists a y, but you don't know which particular y it is.
Well, in this case, we like, yes, you could kind of like, I think if you look at kind of constructive logic, then people say, okay, like, if there exists a y, you have to tell me exactly what y it is. And in this case, we don't really care. We just say, in some sense, we're just, if you look here, we're replacing one existential quantifier by another, right? Instead of saying there exists a value y, we say there exists a function f such that y equals f of x. So in this case, like we're not trying to be constructive at all. The reason we had to use constructive logic was to avoid paradoxes. But here,
you don't need
don't
to
worry about that.
construct the f of x explicitly. You just say
there exists an f, yes. And of course, it would be nice if you know the f. But really, the trick is that you're replacing an existential quantifier for a value into an existential quantifier for a function. And intuitively, that's kind of like, makes sense, right? Like either given an x, I can give you a y. And the way I do that is by assuming there's a function that like, given the x gives you a y, but that still doesn't tell me that like, that I can give you a concrete function for that. And we don't care here about that. In our case, we will always know these functions, but in general, it doesn't have to be. Let's look at a concrete instance of this. Here, like a function is bijective. Whatever, you can look up the definition of a bijective function in your favorite math book or on Wikipedia, whatever. If you use this process of scholomization, you get this kind of, I think, pretty beautiful kind of symmetric definition at the bottom. F of A equals B if and only if A is the inverse of B. And I think the definition on the bottom there really, I think, captures the idea of like a bijection much better than the formula using quantifiers. But of course, that's just me. And maybe you think that the quantifiers are clearer, but I like the one on the bottom. And the reason is that in the one on the bottom, I can now substitute the right side into the left side, because on the right side it says A equals the inverse of F applied to B. If I substitute that in the left side, I get that F of inverse of F of B equals B. And if I substitute the left side into the right side, I get that A equals the inverse of F applied to F of A equals A. So you get, automatically, you get algebraic laws of your functions here that are much harder to see when you're using that non-scholomized version. Does that make sense? So like, and since we want to do algebra, right, we want to have these rules that we can do symbol pushing. And this scholomized version just gives us these rules for free, and they just fall out. So let's apply this to our definition here. So we scolomize this. So for all A, there exists like, a unique value. We just pull the crank. Then we're going to do some more transformations, like we're going to curry and uncurry. We're going to like do some vectorized function application. We eliminate variables, we add some functions here. And now we get to the one in red. And what I'm going to do here is I'm going to substitute A equals 0. I'm going to simplify it. And then we end up in the definition in yellow, or the equality in yellow. And so I skipped a lot of steps here, but what is important here is that I started with this definition of dual numbers. I used columnization and then some standard tricks to make it point-free. And I ended up with the one down at the bottom in yellow. And really, if you look at that carefully, you see that that is exactly of the form of an isomorphism, just like the one I just showed you, like in this slide here. All right, if you look at the bottom here, the form that we get here is exactly that. So that, I think, is quite surprising, that the definition of dual numbers, or the dual numbers property, really is another way of stating that there is an isomorphism. All right. So that is kind of like where we end up. So the dual numbers property is really saying that the pair of two real numbers is isomorphic to functions from epsilon to d, where d are the actual dual numbers. All right. So that's, I think, pretty interesting. And if you look at the lover reals, now you can replace like all the kind of like R and D by the kind of like boldface R, and then you see you get this kind of like weird recursive thing here, and where in our case it is much much simpler. But again, like, you know, modulo the simpler types that we use here, everything still works when you're replacing dual numbers and real numbers just by the lover numbers. So another way of stating axiom 4 is by saying that these two types here are isomorphic, and then these functions alpha and beta, and this triangle gamma, which is got like taking two functions and like distributing the argument over them, pairing them up, that is an isomorphism. And the reason I wanted to have isomorphisms is that they give us algebraic properties. So what we're going to do here is we're going to look at this definition here on the top left, and we're going to do what I did before. I can substitute f that's on the left, I can substitute that in the right-hand side, and I can take the pair of b and capital B and substitute it in the left side. All right, so, and then what we're going to do here is we're going to define what the derivative is in terms of gamma and alpha. And really, there's now no intuition. And this is what I like, right? I started out with maybe giving you some intuition of, oh, there's these, like, you know, nilpotent infinitesimals. They are maybe related to limits and blah, blah, blah. Now I'm just having symbols. And I hope that by now you're completely confused and you say, what do these symbols mean? I lost track of what they mean. That's exactly what I want, because I like intuition-free math. Intuition-free means that you've really reduced it to symbol pushing. You have no idea what these symbols mean. You only know their algebraic properties. And that's exactly what I like. Because intuitions typically don't really carry over, and sometimes they are limiting. Like most intuitions about functions and derivatives only work for simple functions, right? Simple unary functions. Once you go to binary functions, now you have to draw 3D graphs, and it becomes already hard. And then for multivariate functions, it falls down the drain pretty quickly. So I rather have no intuition to start with. all right? So we have one axiom that says that, that there's an isomorphism between pairs of real numbers and functions into dual numbers. That's the axiom. And then I define what a derivative is in terms of these functions here. And now all intuition is out the door. But if you believe me and you've seen all the steps that I've taken, this is exactly the same thing as starting with dual numbers and epsilons and infinitesimals, etc. Only now we have a much more algebraic framework that requires no intuition. All right, so what we're going to do to three properties from this, and one is, that's the middle one, that is comes from the uniqueness, and then the other two come from substituting the like f on the top in the bottom, and the other one is from substituting the pair of b and b into the top. So if we do the last one, we get this property that f equals this kind of like alpha of beta f gamma f. Really what this says is that I can write every function f in terms of this function alpha, right? So it means that every f can be represented in this certain way. And if I do it the other way around, I get that this kind of like fixed point property that like if I have a pair of two numbers, I can like, I would say this one is more useful. The other way around is I can simplify this complicated expression here and drop all the betas and the gammas and just get my pair of b and b. And then the uniqueness property really gives us back a micro cancellation. So these are the three rules that we get. And again, like these just followed from this axiom and nothing that we needed to do. So these are really kind of like theorems that we got for free. They all fell out of this definition of this isomorphism. And remember, we got that isomorphism by doing scolomization and then making the formula variable free, point free. I'll skip this slide. But what I want to show here is that we can go the other way around as well. So based on this new definition, we can reconstruct the dual numbers property that we had before, also by simple calculation. So I just wanted to show here that these formulations are equivalent, right? I can start with the definition of dual numbers, then derive this isomorphism, or I can start with the isomorphism and I get this more familiar definition of derivatives using dual numbers. So this is a trick that you can do in general. As I said, like really maybe the point of this lecture is that if you define your abstraction using a universal property, like we did here, like B of f of A is if and only if P of A and B. Now you can use these properties here, consequences such as like substituting the left in the right and substituting the right in the left, and uniqueness as free theorems, and everything becomes a symbol pushing. And if you look at category theory, this is done a lot, right? Like, you know, people define a lot of properties using, or a lot of concepts using these universal properties. And then you get all these algebraic rules for free, and things become just symbol pushing. And as I said, this is like, you know, a widely used trick from Squiggle. And in category theory, it's got like, you know, used all over the place as well. And what we have shown is that it's even useful to kind of define what differentiation means. And as I said, like everything I've shown you here, I've never used anywhere that these are real numbers or dual numbers. So all these proofs just carry over exactly to lower reals. Now, one of the things here is that I've only done this now for univariate functions. Of course, we want to do multivariate functions as well with multiple parameters. And in this case, since we only have like one identified infinitesimal, what we get is we get confused. We cannot really get like, you know, when we compute the value of f applied to x1 epsilon and x2 epsilon, from the result, we cannot capture the derivative with respect to x1 and the derivative with respect to f2. And we'll like, you know, solve that later. The other thing is that you could now even prove Taylor expansion, right? So Taylor expansion is not something that you use to prove the dual number property. You can use the dual numbers property to prove Taylor expansion. This one here shows that, you know, you need multiple infinitesimals if you want to do functions, multivariate functions. I don't have enough time here, but if you can, like, you know, do that, you can show here Taylor expansion in general from these, from a lower real numbers. So I think that's nice. Often Taylor expansion is a little bit magical, but here you can just prove it using pure algebraic reasoning. So I'm nearly at an hour, so I want to get like finish off here. There's if you look at this synthetic differential geometry, it's very heavy category theory, or very category theory heavy. John Bell, let me just grab my books here. So this is the heavy category theory book from Anders Kok. What I've shown you today here is really just like 2 pages out of this book, expanded into many slides. A much more accessible introduction is John Bell's book, A Primer of Infinitesimal Analysis. He also has a short paper online, and you'll find everything that I've done here, there, except using this universal property, which is in Kok's writings. I'll skip this, I'll skip this, I'll skip that. Let me finish with this, because a lot of mathematicians don't like infinitesimals. And that's, I think, why, like if you look at like Leibniz, he was using infinitesimals and dealing with that informally. And then other mathematicians like this Berkeley guy critique them, and this is how we ended up with limits and so on. But what we can do is we can do another axiom, and this axiom here, which on the right we can prove using dual numbers. But if we take this axiom here, I won't try to like explain it, it's an axiom, and we define derivatives in this way, then we can get, we can compute all the same things like we did before. So we can compute the sum rule, the product rule, everything. But there's no infinitesimals here inside, right? So we only need this axiom, define derivatives like this, same kind of style, same algebraic style. And now we can, you know, derive all the usual rules for derivatives. The downside of this one is that it's not easy to translate this into code. I don't know a way to translate this axiomatization into code. But if you don't like infinitesimals, there is an axiomatization that will allow, will help you with that as well. All right, so I don't have a time to go into integration, but I just want to get, like, you know, show you here is that you can start again with a similar axiom for integration. And again, it looks as for all f, there exists a unique capital F such that some property holds. So this should be now, by now, feel familiar to you. If you turn this into point-free style, like this, now all your rules about integration also become just pure calculations, just like we've done for differentiation. So that is really what I wanted to tell you today, is whenever you define your abstractions using these universal properties, you can turn them into nice algebraic rules, and now you can do just symbol pushing all along. And I think the lesson, like the take home for today, is you can define both integration and differentiation as universal properties, and hence, you know, you can turn all of calculus into algebra, and that's it for today.
Okay, great. Let's all, if you're possible, unmute yourselves and give a round of applause. Thanks to Erik for the great talk. Let's open it up to the audience for any questions you might have. There's also some questions in the chat, but I'll leave it to you. Thanks.
I do have a question. Thank you very much, Erik, for a really nice talk. I'm coming actually from a more geometry background, and I was wondering whether you started with differentiation and integration, and then you somehow moved quickly into defining real numbers. But from a geometrical point of view, we will like more thinking about differentiation and integration as a function or an operator, if you want, on the ring or a set or a ring, whatever makes sense to you, on the functions on that space. So, for example, you might well have the ring of polynomials over integers, and it does make sense to define differentiation there in integration as an inverse operation. And in that sense, differentiation will respect the linear structure of the ring and the Leibniz rule, and the integration will be the inverse. So why not taking that point of view on differentiation integration?
That is a great question, and I would say if you carefully look, what I did is that I really make very little assumptions about the underlying the structure on the underlying real numbers, right? Literally, I kind of like assume that these are like that it's a ring, and so yes, you can kind of like, you know, I think what you're saying will apply here as well. So it is not limited to just real numbers. You can define integration and differentiation in a much more general way. And I think the trick really is to like be very careful with what you assume. It's like, in some sense, this definition is like, in computer science terms, you can make it into a generic function, right? You don't have to get like, you know, I've shown you here for specifically instantiated to reals, but really it is more like a parameterized thing, and it will apply to a much wider set of underlying values. But I think maybe you also make my point is that if you want to do that, like, and maybe for some people it's true, but not for me, is now your intuition gets blurred, right? Because what does it mean if you're taking polynomials? Like, what does, like, you know, now my, like, you know, like a tangent line, what does that mean, right? So I don't know anymore. So that's why I like this axiomatic approach, because it takes away all the intuition, and that makes it easier to generalize, because you're not tied to one specific instance, which is usually what intuition is.
Well, the geometrical intuition behind this is that if you look at the ring of functions on a space, then this is essentially, you can think about the functions as defining subspaces of that space. And then derivatives of that functions will be tangent spaces to those subspaces. So that's our view. And yes, in algebraic geometry, we have the notion of an ideal, and then the tangent space will be the ideal divided by the ideal squared, and then you can play around with this intuition. But then this enables you to move away from defining, like trying to define those real numbers, because as you've seen, it's a very complicated matter, and it's somewhat easier to define just a smaller set of functions you would like to work with that form a ring, and then to define your derivatives on those functions. And yeah, but that's just a point of view.
No. I totally agree with you. Let me give you an example. I'm working on this right now, right? Because really you can, and there's many, if you look at Koch's book, he kind of like generalizes this thing also, you know, probably you've read that book if you're like, you know, into algebraic geometry. But one thing is like, you can say, like, you can define the axiom also over modules. Right, so now you can say, okay, like modules, like we have, like, you know, like vectors are modules or whatever, but you can also say functions are modules. So you get calculus of variations follows exactly from this as well. You don't have to do anything special. You just take this axiom, and now you can generalize it to calculus of variations, where people either can, like, you know, go and have to get like do very complicated things because they have to define metrics over functions and so on if they want to talk about it in terms of limits. Or as the physicists do, they kind of wave their hands and they kind of introduce infinitesimals themselves. But here it just falls out cleanly just from these axioms and the fact that it's not kind of like, you know, just defined on like these numbers, but you can define the axioms on like higher level structures.
Actually, to defend the physicists, you know, they also like defining those Taylor series that don't converge. And in that sense, they still want to take derivatives of those formal series. And in that sense, an algebraic definition of a derivative in integral is helping them, because analytically, the thing just doesn't make sense, because they can compute the Taylor expansion up to some order, but then obviously you can't switch the sum and the limit.
Yep.
In that sense, yeah, the real calculus definition that we learn in first year course in maths is somewhat it's a big problem even for mathematicians later and physicists included.
Yep, I agree. So, but it's kind of like, you know, strange that we're still teaching that, right? Like, and then people have to kind of unlearn in some sense. They have to kind of generalize. I rather kind of like have that we kind of teach people the more kind of like, you know, abstract definition, and then like, you know, the normal definition is just an instance of that. But I think that's not the way I don't think it's ever going to happen, but we'll see.
Thank you.
So I know there's some questions in this chat as well. I could probably address.
Where do I see the chat? Oh, here.
Well,
the chat. I can see it
looking
here.
for a link to the work on CPS that you mentioned. I guess I can include that towards the end. But there's different implementations, I guess, of infinitesimal free calculus in different languages. I guess you're probably aware of different computer algebra systems and things like this. I was wondering if you could, well, maybe comment on that and or how you're, or if you're familiar with other frameworks and how your implementation, your concrete implementation, you know, any issues that you ran into implementing this in say in Python or in Kotlin, the language itself, whether you need certain language features to do this, or some of the when you lowered this onto the computer, or some of the issues that you ran into.
Yeah, I think the main thing I would say is how do you, like the simple example I gave, like, you know, for like, you know, sine and cosine, right? Like in order to extend a function or take some function and make it overloadable on dual numbers or whatever, right? Or make it kind of differentiable. That is really like an API problem. And especially if you're doing backwards AD, now you have to give both the forward and the backwards rule. And how do you make that like, you know, easy to do? I think is really the main thing.
So for sine and cosine, those were the you gave some examples. Do you need those as axioms, or can you reconstruct those through this algebra that you've defined?
No, here I needed them as axioms, right? Because like if you want to take the derivative of cosine, really what intuitively, like, you know, like then you need to know how it extends to dual numbers. And in order to do that, you have to specify how it behaves when you give it just like, you know, the most trivial dual number, right? And now, but if you do, and that's the, like, you know, the kind of API design. If you implement this for real, how do you do this? And especially if you go to backwards AD, now if you have some function and you want to make that kind of like differentiable, you have to tell it, like, you know, how to differentiate it. So you have to tell it like how it behaves forward and backwards. And you see this a lot. You saw this like in Swift for TensorFlow. And JAX, there was a talk recently at, I think, Rebase or one conference from the JAX folks on how they do that. So I think that is really the kind of like biggest thing. The other thing is, do you need higher order derivatives or not? And how easy do you make that? And then the other thing I would say is, and that's very unsatisfactory. And maybe I think Connell, like by staying in like a category tier world, he kind of like avoids it. But most of the time, if you're doing backwards AD for sharing, you suddenly introduce mutable state, because you have to get like, you know, like if there's two backwards computations, like, you know, you have to get like update something in your graph. And so you're kind of accumulating the gradients, and now things become like stateful, and now you have to null out things and so on. And that's not a nice design. So can you make a design that's like that use backwards AD, but where you don't see the state? that is like, I think, one of the things that, you know, we ran into as well. Because otherwise the implementation is staring you in the face. And I think a lot of like Python based AD frameworks, this statefulness kind of like shows up right in the API. And that can bite you if you do, like they go to big lengths to get like null out the get like things for you under the covers, but sometimes you can get space leaks or something if that doesn't work.
Yeah, it seems like you kind of avoided some of the issues with inheritance, and you kind of mentioned, you know, that this is a problem with the numerical tower that some languages have, like the Lisps and so on. So you have this isomorphism with the reals that you're kind of really concerned about. Do you know or do you have plans to extend this to other number systems, or do you think that's not very important?
So that is kind of like, you know, I think interesting, right? Like this was I think was Roland's kind of question, and you see this also, like everybody's trying to do this, right? You want to kind of like, you know, like not have just derivatives over functions, like unary functions from real to reals. You want to do it over functions, multivariate functions over functions that take matrices. You want to do it on like arbitrary data structures that have like floating point numbers embedded in them, and then you can call them like whatever, like manifolds or something. You want to do this over functions. So you do want to abstract these things, absolutely. But as always, kind of like abstractions come with a price as well. And so it's like, you know, do you really need the generality or don't you need it? And that is always a balance. And because you can also, like, abstraction can also move to the extreme where you're really abstracting over everything, and you never instantiate over more than two things, then you should have probably not have done the abstraction.
Yeah, that's good food for thought there, I think. I know we've already kind of gone over by a few minutes, but last call for questions from the audience. I don't know if anybody else any pressing questions you'd like to ask Erik. Well, in that case, we'll try to put some links with your talk, if possible, along with the slides. We have some good books that you mentioned by Anders Koch and John Bell. Hopefully, I'll put those in there, and we'll put a link if you want to reach out to Erik about any further questions. This is really great. Thanks so much for taking the time to speak with us today. I know it's really something that I think a lot of people are interested in, and hopefully we'll get some more research in this direction in the future. Looking forward to hearing more about that. I'll end the recording now. Thanks.
All right, thanks. Bye.